Hi everybody, this is Shiva Biram signing in. In this session, I would like to explain you the importance of speed time curves, what is meant by a speed time curve, and different types of speed time curves. Before going to know the speed time curves, let us see the different types of services we are going to have in electric traction. Depending upon the traffic density and the distance between the two stops, the services in electrical traction have been divided into three: urban services, suburban services, and mainline services. This classification has been made depending upon the distance and the traffic density of the route. Let me explain you the urban city services. In these services, the distance between the two stops is very small, about 1 kilometer. And in order to achieve this speed schedule, we need to have the motors of high acceleration and high retardation. And for the suburban services, the distance between the two stops is relatively longer compared to the previous urban services. It is about 2 kilometers to 3.5 kilometers. And here also the motors require high acceleration and retardation. For mainline services, here the distance between the two stops will be a little bit longer compared to the previous two services, that is urban and suburban. Here approximately it will be of the order of 10 kilometers between the two stops, and here that much acceleration is not required for the motors that we use. So here the total running time will be more as compared to the accelerating time. So if we have the characteristics for urban services, the acceleration will be of the order of 1.5 to 4 km per hour per second. Actually, in case of electrical traction, the acceleration and retardation are going to be measured in kmph ps, kilometer per hour per second, because all the derivations we are going to do further, they will be based upon these units only. So it is very important to remember the units also here. The acceleration and retardation are going to be specified in kmph ps, and the speed will be specified in kmph. So here the retardation will be between from 3 to 4, and maximum speed 120 kmph, and the distance will be 1 kilometer. Similarly, for suburban services, the rate of acceleration and deceleration will be of these values. The distance will be 2 to 3.5, and for mainline services, the acceleration will be 0.6 to 0.8. It is typed wrongly. 0.6 to 0.8 kmph ps, and 1.5 will be the retardation, and the maximum speed will be a little bit more compared to the previous services, and the distance will be greater than 10 kilometers. Now let me explain what is meant by a speed time curve. It is the curve drawn between considering time on x-axis and the speed on y-axis, and the area of this speed time curve is going to give us the distance traveled between two stops. This is the exact speed time curve we are going to have. Let us suppose that the vehicle or the train is going to move from t is equal to 0. So this is the time we have considered on x-axis, and the speed in kilometers per hour on y-axis. We have different instants of time during the travel from this point to this point. From 0 to t1, the vehicle is having more values of speed, means it is accelerating, and from 1 to 2, or between t1 and t2, it is further having increased values of speed but a little bit lower, and from 2 to 3 it is moving with constant speed, and from during this duration 4, from t3 to t4, the vehicle is allowed to move on its own inertia, means this is known as coasting. Here the supply will be cut off and the train will be allowed to move on its own momentum or inertia. And at point t4, at this period the brakes are applied, and this instant is known as braking period. These are the different parts of a speed time curve that generally we consider for a mainline service. So the first part is considered as notching up or rheostatic acceleration, because here the train accelerates, and second part is acceleration on speed curve. Third one is free running time or free running curve. Fourth one coasting or coasting retardation, and fifth one is braking. And when you consider for urban or suburban services, here we have only acceleration, coasting and braking. Here we don't have the free running time. So here also we are going to have the same for suburban services, same as that of the urban services. And let me explain you the different parts of the speed time curve. The first one is notching up or rheostatic acceleration. So during this period, what actually happens is the starter resistance of the motor is slowly cut off, gradually cut off, so that the train gains the speed slowly. Obviously it is going to accelerate. So that is the reason why this is considered as notching up or rheostatic acceleration. During this period we are going to cut off the resistance of the starters. So here the handle of the rheostat will move from one notch to the other, and hence this is considered as notching up. Here the average torque developed will be constant, and acceleration also remains constant, because we are going to have the same intervals of the same increment in the speed levels with respect to time, hence the acceleration remains constant. Almost all it will be a straight line. The second one is acceleration on speed curves. Here during this period the train will be still accelerating, but not the shape will not be a straight line. Here the acceleration is possible because of the applied force will be more than the train resistance. So here that complete resistance of the motor is cut off, and the voltage remains same. The effort exerted by the motor is more than the train resistance. This is the reason because of which the acceleration is still possible at this instant. And third one is free running curve. During this period the train moves with the constant speed, which is also known as maximum speed measured in kilometers per hour. During this instant the motor draws constant power. And coasting period, here the supply to the train will be cut off, and the vehicle is allowed to move on its own inertia, hence it is considered as coasting period. During this, as the supply has been switched off, there will be retardation for the vehicle, the vehicle experiences retardation. So the speed decreases due to the train resistance. And braking period, during from T4 to T5 the brakes are applied at this instant, hence the vehicle is going to decelerate, or the speed decreases uniformly. And that's about the different parts of a curve. Next, the important point of discussion is average speed. So average speed is nothing but it is the ratio between the distance traveled, the total distance traveled between two stops, and the time taken for the travel. Generally the distance is going to be measured in kilometers, and the time will be measured in hours. So if you consider the formula for this, it is represented by VA measured in kmph, kilometers per hour. So VA will be equal to the distance between the two stops divided by the actual time of run in hours, which is equal to D by T. So here you can observe distance traveled divided by time. Generally for traction applications the time will be measured in seconds, hence T will be in seconds. And if you convert that seconds into hours, 1 second will be equal to 1 by 3600. So 1 by 3600 will become 3600, it will come to the numerator. Hence the formula for the average speed becomes equal to 3600 d by t, and it is measured in kilometers per hour. Similarly, we have got one more definition, which is scheduled speed or scheduled speed. Here it is the ratio between the distance between the two stops and the total time of run, including the time of stop. So in previously when we considered the average speed, there we have considered only the time of run between the two stops, but here in scheduled speed we are going to consider the time of stop the train has got during that particular travel. So always it is very clear that the scheduled speed will be always less than the average speed. It is represented by Vs and measured in kilometers per hour. Hence we can write the formula for scheduled speed as distance between the two stops divided by actual time of run plus time for stop. It is the duration for which the train will be in stop position or rest position between that journey, during that journey. Hence d by capital T plus Ts. Here if you observe that in the denominator we are going to have T plus Ts. Here Ts is the time of stop, and if it is represented in hours, we are going to get 3600 in the numerator. So we are going to have the formula Vs as equal to 3600 d by T plus Ts. So in this formula for scheduled speed we are going to have d in the numerator and time in the denominator. So next, let us go through the different factors which are going to affect the scheduled speed. And acceleration and retardation. Generally acceleration is going to be represented by alpha and retardation is going to be represented by beta for all traction applications. So alpha means here both alpha and beta are represented in kmph ps, kilometer per hour and per hour per second. So let us see how these alpha and beta are going to affect the values of scheduled speed. And next one is maximum speed, and finally duration of stop. So let us see how these factors are going to influence the scheduled speed. First, effect of acceleration and retardation. So when you consider a particular distance between two stations, if you greater the value of acceleration and retardation, what actually happens is the total time of run to cover the distance is going to increase. Similarly, if you decrease the value of acceleration or retardation, the total time taken for that run is going to be increased. As we know that the scheduled speed is going to have the inversely relation in between time with respect to time. Obviously, if you increase the value of acceleration, obviously the scheduled speed also increases because of the lower values of time. So that is very clear. We are going to have the proportional relationship between the scheduled speed and the acceleration or retardation. Similarly, maximum speed. This maximum speed also is going to have the same relation. If you increase the value of maximum speed, the total time of run to cover the distance is going to decrease. So if you can consider two cases where the maximum speed is in one case 50 kmph and in another case say 75 kmph. Obviously, in the case of the second case, as the speed is more and the distance is constant, the time of run will be decreased in this case too. Obviously, as the time is decreased, the scheduled speed is going to increase because there is an inversely proportionality between the scheduled speed and the time taken. So obviously, with more value of maximum speed, lesser will be the time of run and more will be the scheduled speed. And duration of stop, it is very clear. Generally, in the definition itself, we are going to have the duration of stop in the denominator. Obviously, there is an inversely proportionality between the scheduled speed and the duration of stop. So, if the duration of stop increases, the scheduled speed decreases, and vice versa. So, that's about the definition. I mean, average speed and scheduled speed. Actually, with the exact value of with the exact shape of, if you consider the exact shape of speed time curve, that is right from the notching up or rheostatic acceleration, acceleration on free curve, free running time, coasting retardation. So there are different five parts of 5 parts are there, 5 segments are there in the exact speed time curve if you consider. But with that speed time curve, if you go for the calculations regarding electric traction, it becomes very difficult to simplify. That is the reason why the speed time curves have been simplified into two categories. One is trapezoidal speed time curve, another one is quadrilateral speed time curve. During this simplification, we should take care such that the values, the results will not be that much deviated. So trapezoidal speed time curve is the first approximation which has been done, and second one is quadrilateral speed time curve. So these are the two approximated speed time curves which are also known as simplified curves, and this simplification has been done because of the difficulty in solving the exact speed time curves. So in case of simplified trapezoidal speed time curve, the running and coasting periods, so whatever running and coasting periods are there, they are replaced by a constant speed line. And in the case of simplified quadrilateral speed time curve, the running and coasting periods are extended. The free running and coasting periods are extended like this. So obviously we are going to have a drooping characteristic like this. And remember, whatever approximations we are doing, whatever simplified speed time curves we are considering, during that the total area should be remained as same. That is, before approximation, whatever area we have considered, after approximation also, whether it may be either trapezoidal or quadrilateral speed time curve, that the area covered should be the same in both the curves. So this is actually the trapezoidal speed time curve. So here this white line indicates the exact speed time curve, and the black line, whatever black line is there, black path is there, this is going to represent simplified trapezoidal speed time curve. And you can observe that the area in both the curves, before approximation and after approximation, remains the same. So we have got only three parts. One is acceleration, second one is free running time, and third one is retardation. So in trapezoidal speed time curve, we have got only three parts of the speed time curve. One is acceleration, second one is free running time, and third one is retardation. So obviously the calculations becomes very simple, and the results will not be that much deviated from the exact values. Hence we can consider this trapezoidal speed time curve for the calculation purpose. And similarly quadrilateral, so here also this part is going to be replaced by this black curve or black quadrilateral, and here also we can observe that the complete area before approximation and after approximation will remain the same. Here we give, in this quadrilateral speed time curve, we have got three parts here also. One is acceleration, coasting, and another one is retardation. From O to A, that is the duration for T1, it is considered accelerating period, and from A to B, so here at the end of A we are going to have maximum speed V1. Let us consider it as V1, and after at this point we are going to switch off the supply, so the train retards slowly from A to B, and at B we are going during this travel from A to B, the vehicle moves on its own inertia, hence it retards. This period is considered as coasting retardation, and after reaching the speed V2, which is the minimum speed, I mean at the end of T2, we have the speed V2. We apply the brakes, hence the train retards and come to the rest position at this C. So V1 at speed at A in kmph and V2 speed at B in kmph, and OA is the acceleration, AB is the coasting retardation which is considered as beta C, and BC is the braking retardation beta. So beta C is the coasting retardation. Here we are, whatever retardation the vehicle is going to experience between A and B, it is considered as coasting retardation. It is expressed in kmph/ps. So this should be kmph/ps. And T2 is the time of coasting. So these things we are going to, whatever derivations are there with respect to this simplified speed time curves, that is quadrilateral speed time curve and trapezoidal speed time curve, we are going to see in the next sessions. So that's about this session. Dear viewers, please subscribe to my channel and share your valuable feedback. That is going to help me a lot in making my videos in a better way further. Thank you very much. Thank you for watching. This is Shiva Beenam signing off.